Welcome to the Complexity Workshop. In this workshop, you'll have the chance to build a static analyzer for code. Now, it may seem that this would be something pretty difficult to do, but I'll tell you that this is actually much easier than it looks and fun. And bonus, many of the things you'll implement will be useful in a technical interview. So let's get started by doing the familiar cloning or importing the workshop and installing our dependencies. So everything's set up. But let's start with thinking about why won't we use something else, another type of approach? Why are we doing static analysis with the things that we're about to do? Well, why can't we just use something like regex, for example? Um, so besides the standard answer for not parsing HTML with the regex, I think it could be illustrated with a really simple example of a common analysis that you might want to do. So for example, imagine you wanted to detect message changes in code, which basically involve looking at statements and looking at how long they are, right? So here we see a string that says a fairly long message change with lots of data accesses, right? So this could easily be detected by just having something that just counts the number of dots in a line, right? And so it would seem like that would work pretty well. Uh, so we could do something like this where we just split each line in a file and then check for if it has a dot. And if so, we just split the, the line up and count to see how long it is. And then we could implement this, put it inside a build pipeline and say that if we ever detect a message change that's longer than X, say 4, then we will fail to build, right? So this could be an example of a static analysis that you could put into code. So let's run this and see what would happen in practice. So if we look at what this code ends up detecting, we'll see that we did get this first one. We could see that it found 10 a 10 long message chain. But then we also noticed that it picked up this one, which was just a message that happened to have dots. And that has nothing to do with message chains. And we also noticed that it didn't pick up this other one that happened to use new lines, which incidentally enough is actually fairly common to write these things. And so my main point here is while regex seemed like an appealing option, you'll find that it quickly breaks down. And you may think that, well, the answer is just to throw more things at it, more regex is the solution to regex is more regex. And you could do that. And I will promise it will not end well, because ultimately what will happen is that you will build a static analysis technique that results in both high false positives. That means it's detecting things that aren't a problem, and high false negatives. That means it's missing the things that it was actually supposed to detect. And what you're going to find is if you put something like this in a build CI pipeline, you're going to find a angry mob of programmers coming after you, insisting that you remove this right away because it's just really wrong. And I'm not making this up in the sense of that this is actually well known in the static analysis community. And a really good read on this is a few billion lines of code later using static analysis to find bugs in the real world, which was written by Coverity in their kind of quest to make static analysis actually work in practice. And being able to handle false positives and false negatives was a huge part of this. And they don't, I can tell you, they don't use regex to build their product. They actually parse the code, right? And so that's what we're going to do. So instead of treating the code as a string of characters that we match with a simple state machine, we'll actually turn, using a lectern parser, turn those characters into tokens and then organize those tokens into a representation called an abstract syntax tree. And while it's possible to write that by hand, we can actually take advantage of a simple package for JavaScript that will do this, esprima. So if I run this and you see them porting esprima, and it's parsing this really simple expression, it will actually turn this into a object representation, so a JSON structure that's basically a tree that has all the tokens, like a body token and a value, which is a list. So this would be a list of statements, a type token, a variable declaration token, and then which is made of these parts, which is a list of declarators, which has an identifier, binary expression, et cetera, right? So this, as you can see, this actually already is starting to look a little bit complicated. Here's a little statement, and all this stuff is here. But I promise you, this is actually better. So we could, if you need to understand more, which you will as you kind of analyze some things in the workshop, you'll be able to use this interactive component here, which is just an interactive version of Esprima, their parser online, where you could just type in stuff, and it will actually show you um, what this looks like under the hood. All right, so let's walk through this real quickly. So again, you see that there's a function with an if statement and some return statements. And we'll see that this tree representation basically has a program and a body. And then that has a function declaration and then here's all the properties of that. And inside the function declaration is a body that has a block statement, an if statement, member expressions, et cetera. Right? So this tree gets pretty complicated. But if you also wanted to look at it as just the literal stream of tokens that it comprises of, you can also kind of look at that. And that's actually pretty helpful just to know, how would you translate a piece of text into its corresponding token? So, and the actual thing that you would work with programmatically would look like this. So this is not as easy to understand sometimes as the tree view or the token view. So this will help you understand how a piece of code and its corresponding syntax tree will look like. But how is it we're going to actually use this to do what we want? All right, so we have some code already set up for performing really basic parsing and just setting up the workflow you would need for parsing code. But I need to cover two design patterns before we go further. The first is the visitor pattern. And if you're not familiar with this pattern, the main idea is that if there's a complicated data structure as the one that you just saw above, you may not really know how to navigate and perform actions on it. And what the visitor pattern does is it basically implements a traversal of that data structure so that you'll actually visit every element of that data structure. But what is different is it will emit an event, or it will basically have a callback that says, hey, look, I found a method node. And if you're interested in subscribing or receiving updates about methods, then you can essentially write something that will respond to whenever a method node is visited and do some sort of analysis. So that is going to be super useful for allowing us to go through the AST without really needing to know how its real tree representation is. The second is a builder pattern. And the main idea of a builder pattern is it's useful for collecting incremental results as you are in the middle of processing something and deferring a final calculation that you want to do. A really good example of this is in graphics. So in graphics libraries, you may want to incrementally build up a scene, like say, draw a line or a circle, and you plot kind of, here's the start point, here's the end point. I'm going to fill in, I'm going to color the line a certain color. I'm going to fill in the vertices with a certain fill color. I'm going to make it transparent. And then you will see kind of this incremental adding to the code as kind of like, statement after statement, or just basically emitting. But when you're done, you basically say, I'm done with building up the scene, and I'm going to send out this request to the graphics pipeline. And you see similar stuff for writing HTML dynamically, of where you'll say, I'm going to open up a new div and then add some elements to it and not worry about stuff like appending a literal end slash div to the end of something, right? So the idea of the builder pattern is it provides a framework for you to be able to build up an object and not worry about like its internal representation you need for maintaining its state. And then you have an easy way to say that this is what I'm doing when I'm done. Now, we're not using a builder pattern really extensively in the sense of taking advantage of all those things, but it's kind of the best name for the what we're using here. So let's look in more detail at some of what we're doing. So imagine let's go with a really simple use case of we wanted to build a simple analysis that would check whenever a method had exceeded a more than a certain number of lines of code. So basically, let's build something that can check if a method has more than 100 lines of code. And if that's the case, let's reject it, right? So how would you build something like that? Okay, so not regex. What else? All right, so we're going to use the AST that we get, but with the visitor pattern, we're going to basically do what we talked about before. We're going to just listen to when we get function declarations, right? And so if you look at this piece of code, which just says print function links, where we're just checking to see how long each function is, we're using this function called traverse with parents. And traverse with parents is implementing the visitor pattern. What it's doing in its initial call is receiving the AST, and then it's calling back this function. What's a little bit weird about this is instead of calling this back one time, like you might expect if I make a web request and I get a callback, it's actually calling this back multiple times. In fact, for each node of the tree. And what will happen is that I could use this logic to do something like, all right, whenever the node type is a function, then I want to run my code, right? And eventually, because you visit all nodes, you will eventually hit all the function declarations and you can calculate everything that you need. In this case, I could just use the end and start line properties that esprima has collected for me to calculate the length and print that out. So you could see that this results in surprisingly powerful and compact code. Imagine how difficult it would be to write regexes for doing this. And then the fact that this may not even handle things like nested functions or all the other crazy stuff you could do in JavaScript. So this is actually really easy and straightforward code to write. But it turns out that to kind of use this in practice, you kind of need to do a couple things. So we'll go over that. So as we're visiting each of the AST nodes, the way that we're going to collect this information is we're going to use these builders that are in the code to store the results. And so, for example, if we want to store, all the strings or packages that we encounter or the complexity metrics that we're going to be measuring, then we could store it in the builder. And then when we're finally done, then we are going to use this report method to calculate the results. And you'll actually see that if you look in the code, the function builder is a lot more complicated than this. All right, so for this workshop, we're going to run this function that's called node analysis. Okay, I extended it so that you should be actually running it on this. Okay, so what this does is this node analysis will take in a given file, so this code.js file, and it is basically just running this on it's going through and it's reporting facts about the file and facts about each function, right? So that's kind of what the base code does. All right. And what we're going to do for the rest of the workshop is we're going to extend the code so we actually can fill these inks so they're not just zeros, because right now there's kind of placeholders, right? And so to start off real simple, what we're going to try calculating is something as simple as just counting all the strings in the entire code file, right? So I am going to refer to you this little cell right here where I can run a tiny esprima block where you could see a syntax tree real easy. So for example, if I'm looking for how does a string get represented in esprima, then I could look down and see that there's this var. Here's a string, right? So right now I can see that it's using a literal type, right? So if we go back to like this code, it would be node.type equals literal, right? So that's what we're looking for. Okay, so using this AST printout could be a real quick way to understanding the structure of the code and the tokens that you're looking for. You can also go back and use this. All right, so that's my recommendation for if you need to explore how the code looks like. But I went ahead and decided just to go ahead and let you code in this file here. So I'd suggest opening up a code window and going in here. So this complexity function to start plugging in stuff, right? So we're going to be working with the same visitor that we had before, like that traverse with parents, and it's going to get an AST and its node. And we're going to start with a real simple string calculation. So I'm going to store in the file builder strings. I'm just going to put something there just so that we see something happen. Okay, so imagine I decided that it should have 100 for whatever reason. And you'll see that it now will report 100, right? So my goal is to actually make that accurate, right? So how do we actually make this work? So, all right, so my goal is to check if the node type equals literal, then I'm just going to take this and increment it by 1, right? Because I found another string. All right, so I'm running that, and I'll see that it says I had 145. Wow, that's a lot of strings in this code. All right, but one thing to note is that though if we look back at this output here, where it says that this string here is a literal, you also notice that it treats numbers as literals too. So we actually need to refine this. So this needs to be, instead of just if it's literal, it needs to be and the node dot, so I could see here, init, or wait, in the node dot type and then the node dot value is 5. So if the node dot value, so the type of that equals string, and it's literal, then that should just be just the strings. All right, so now we see that it's a little bit smaller, 103. It was actually close to 100. Maybe I should have just went with that. Okay, so that's one thing already down. Now, the reason I'm doing this, something really simple, is just to show you like, how simple it is to calculate something like that. But how might this be useful? Well, it could actually be useful to calculate the number of strings in a file as kind of like a code smell detection, just in that if you're having a lot of literal strings, that could represent some sort of design flaw. And it might be interesting just to calculate that across your code. And you can see, if you wanted to look at the code under test, here's all the stuff going on. So you can peek at that. All right, but what about the next thing? So the next thing is to calculate package complexity. So there's actually research that shows that you could predict how likely a defect is going to be in a code base based on the type of packages it imports, so that some packages are more likely to lead to bugs, and the number of packages. So it's a kind of interesting surrogate for complexity of a file. And all it does is just basically see how many packages are you importing, right? So if we wanted to actually calculate that, how might we do it? So I refer you again to doing something like this, where I'll just take this and do a require. Okay, so there's an import statement. And how does it look like? All right, so, oh, okay, it turns out there's no like import node or something. They're kind of all just really basic. So instead, what I'm going to have to do is I'm going to have to check for call expressions and check for when the its callee type is a identifier and the name is require. So it's kind of that that will be my strategy here. Now you could do all sorts of crazy stuff, like you could, try to match the higher level version of the tree, like the fact that it's going to have a variable declaration and be assigned all that. But then keep in mind, you can also do something like this, where you can assign multiple things, right? And you can also require right in the middle of a statement, right? So this is not going to be accurate if you try to overmatch on the whole tree by just matching on this part of this subtree of the AST is sufficient for what we're trying to do. So that's what we're going to do. So what I'm going to look for here is node types equals to a call expression, and when the node.callee.type all right, and we're just going to be dangerous and just go ahead and say callee dot name equals require. All right, a little bit messy, but we'll go with it. Power Builder import count plus plus. All right, let's see if that works. Okay, so we go back up and it says 4 packages. So let's look at the code, see if that makes sense. All right, well, I see 2 packages. Did we mess something up? Well, if I scroll down a little bit, also see there's a require here and a require here. So that seems about right. So we actually got all the requires that were in this code. So that worked out pretty well. Okay, so we actually already did this part and that was pretty easy. But let's do something that is going to be a little bit more nuanced, where we look at, instead of just things in across the file, we're going to look at things that are specific to the functions. So what we're going to have to do is we're going to actually have to be inside this part of the visitor where we're actually within the function declaration, right? So we will have to do something here to calculate what the number of parameters are, right? So we're going to be looking at how many the number of parameters in each function and the number of lines of each function. So let's go back up here because we already had a function body here and look at how this looks like. So we see function declaration as an identifier, name. Okay, params. So this params field looks like that's going to be useful. And it looks like it has an array. So that's going to be showing us how many parameters it has. So that one is easy. And what about length? All right, well, so this doesn't show it, but if I click line and column-based node location, then it will actually change this so that this function declaration will have a start and end. So it has a All right. I think that's talking about just the function name. So we're going to want to make sure we grab the right thing. Anyways, so this is a start though. So let's look at builder and we're going to be doing parameter count. And we basically want to set this equal to the number of parameters in the function. So remember, how do I find that again? So it's just going to be, remember, I'm inside a function declaration node and looking at its params property, right? So there's a params property. That is an array, so I could just take its length. Let's try that. Okay, it looks like I'm populating this. This is good. So 326. Well, that looks pretty crazy. So let's look at that and see if that makes any sense. So demo does look like it has 3, and then this looks like it has a ton. So that looks about right. So there looks like we're counting parameters. Let's see if we can do the, sorry, let's see if we can get that method length. So we're going to do builder length, where we're going to store this property, and do the node loc end line minus node loc start line. Let's see if that actually gets us what we want. All right. All right. So I can see the length property being filled in. That looks reasonable-ish. So okay, that looks about 4 lines or 8 lines of code. Might be off by 1, but just kind of depends on what they're counting or not. Close enough for me. All right. So you could see this is how we store a really simple statistics about our files and our functions. But we really haven't gotten into the more sophisticated side of the analysis that we can be doing. So I want to introduce you to 2 complexity measures that are pretty popular in static analysis. And the first one is called cyclomatic complexity. It's a very classic measure. Macabre complexity is another name for it. And then the main idea is that you're measuring the complexity of kind of the number of paths that you have to go through. It's not the same as the number of paths, but it's kind of a simplification of that. And it turns out that there is a really complicated formula, or more complicated formula, that involves being able to calculate the graph and looking at kind of, forget the term, but it's like closed sets, and then like, or fully connected components or something like that, and vertices and edges. Well, it actually turns out that there's a simpler way to calculate this, which is just the number of decision statements, which is kind of similar to when we did control flow diagrams, and add 1. It's really that simple. And so, and when you look at it that way, this is actually pretty easy. All you have to do is basically count the number of if statements in a function and then add 1. So that's pretty cool. And then you have this nice metric. The second one is called halstead. So it's an older metric, but it turns out this is actually a really useful metric for better predicting how hard something might be to understand. And there's actually empirical evidence that we did recently in showing this, that shows that for humans, halstead is a better predictor for measuring how the brain works, and like basically how much effort the brain has to put in better correlates with halstead and does not with cyclomatic complexity. That maybe that's useful for looking for errors or something like that. But halstead is useful for cognitive load. And the way that you do this is you calculate the number of symbols and operators in a function. And the kind of idea of this was this idea of kind of like working memory of if you had all these symbols and kind of large vocabulary you kind of maintain in your head as you're reading something, the more that you, if there's like 10 unique symbols in the code, then that means that you have to think about all those things as you understand the code. And so this is actually a really simple way to see, is something hard or not to understand. And so the way that you would have to do this is basically, for the purpose of this workshop, is look for all the unique identifiers and basically variables and binary expressions in the code. So we'll show you how to calculate that in a bit. But here we go. So let me show you my favorite mistake that I always see every people do when they do this. So we're wanting to calculate cyclomatic complexity, and we're going to try to count the number of if statements. So I'm going to do this. And I believe it's this if statement, but we can double check real quick here. There, if statement. Yeah, so type if statement. All right, so if statement. And then what we're going to do is we're going to do the builder for this function where we're going to be collecting stuff. And it has a cyclomatic complexity property. And we're just going to add to that. And there isn't really add one logic, but I'm just going to be cheap and change this so that it's initialized to 1. Run this code. All right, so maybe I did it. Cyclomatic complexity 1, 1, 1, 1. Somehow that doesn't feel right. So I'm not sure if that code actually ran. And let's look at it again. So remember, if node equals function declaration, then we're going to run this stuff and then do if node is equal to if statement. This should work, right? Well, okay, nothing, if you think of it, nothing has happened between this and this to change the node. And if you look at one definition of insanity, if you do the same thing twice and expect different results, that's in one way insane. So why would this work? We haven't done anything to change how we visit the code. We basically were given by our visitor pattern here's your function node, but we don't have any mechanism for saying, I would like to explore more and find if statements now, right? And so that's where we need to bring in the concept of a new visitor. So luckily I have this up here and I can copy it, go here, and then say, okay, let me run this again. All right, and this is still sort of a mistake, but I'm gonna go with it, see what happens. All right. So now I'm seeing, oh, okay, something that looks a little bit better. 16, 16, 16. Wait, why is it all 16? All right, well, I sort of just was a little bit crazy here. If you actually think about what we're doing here, is we're traversing the whole program, the whole file. Then we're saying if we hit a function declaration, we actually want to start back up on the top and traverse it all over again, but this time checking for if statements. So what this has done in effect is count if statements of the whole program, and we don't want that either. So what is it that we actually want? We want to change this to be the actual node that we want to visit. So this, we want to say that within this function, please let's visit everything in there. And if the child node that I visit is an if statement, then let's count plus plus, right? This is actually incredibly simple code, but you can see that if you get those details slightly wrong, then it does something that's weird. All right, this looks a little bit more reasonable. 8, 6, 1, 2. All right, well, let's look at what is decision and functioning to see if that makes sense. So we see here, there's one if statement. So number of decisions plus 1. So 1, 1 plus 1. So the 2, 2. Okay, that makes sense. There's no if statements here. So read statement just has 1. Okay, so that looks roughly right. Okay, so that, and you can go into more detail. I think demo has 6. Let's look. That 1, 2, 3, 4, 5 plus 1, 6. Okay, so cyclomatic complexity 6. Now remember, cyclomatic complexity doesn't care about the structure at all. It just compares of the number of decisions. Okay, so you can start to see how all this works. You basically have all the pieces that you need to start building more and more complex techniques for analyzing code. And it turns out that almost none of them are longer than a couple lines of code, right? We were able to implement a lot of these techniques, these measures with really simple things. So on your own, I'm going to want you to do the simple halstead and see if you can figure that out. And then I'm going to point out this more complex set of metrics. One is looking at the max conditions. So if you saw, I think the good one was here, where you see this is decision node, which is actually useful for checking to see more than just the if statements or anything, like, because for loops and stuff like that actually count in cyclomatic complexity. So you actually probably want to use this. But anyways, if you look at each one of these, this is considered a condition, right? So if you go, remember back to condition coverage, if you counted the number of conditions in this code, 1, 2, 3, 4, 5, right? So this would have 5. So if I were to say, if there was another if statement in here, what is the max number of conditions in a function? 5, right? So that would be the result. The second one, max nesting depth, is actually checking to see how deep into a code that you go. So if you look, it's not the number of if statements, it's how deep they get nested. So you see this is an if statement, then it has another one, and then another one. So if you're inside this leaf, or inside this statement here, then this is nested within 3 if statements. So the goal of this analysis is to check how far are you nesting in, and what's the longest of all of them. Because you notice here you're just 1, right? And so you want to pick what is the max nesting of a particular function. And that is obviously useful for all sorts of stuff, like potentially looking for unoptimized code of where your algorithm is probably too complicated, especially if those were, say, for loops. It could be useful for all sorts of, once you get to a certain level of nesting, you kind of wonder if you need to refactor or simplify that code or logic. So it could be really useful for static analysis for just kind of screening for potentially over complex code. And it turns out calculating this is going to be a little bit different than some of the other things. And so my strategy for doing this is to do something like this. Visit each node until you reach a leaf, which is basically whenever the number of children of a node is 0, and there's a helper function for calculating that. Then you traverse back up the tree from that leaf node using the parent property, which is actually part of each node. Each node has a parent property. So this lets you climb back up the tree. And then you count the number of parents along the way as you're climbing up that tree that are decision nodes, right? And so if we were to walk through this, if I hit this statement, and then I say, okay, there are no more children to visit, so I'm gonna climb up. And my parent is this if statement. And then I would climb back up to this function, and then I would say I'm done, right? And the length of that was 1, right? And then now I'm still visiting all these other things, because remember, I'm visiting every node. And then here, I visit this guy. This one has no children. So I go up and up and up and up. And then I'm done. And the length of that was 3. And if you use basically a kind of max storage logic of where you always replace the largest value as you discover it, then you could build a really simple, in a couple lines of code, it's actually not that complicated, for calculating max nesting depth. While you don't have to do this for this workshop, you will certainly have to do something like this for the project. So it's better to just go ahead and figure this out in code like this while you have the chance. And sometimes this has appeared on the final exam, so also good to practice this. So I'm going to stop here for the workshop, but you basically have everything you need to be able to try to follow along and implement some of these properties. And eventually you will be using this code to run on within the milestone and integrate it within the pipeline to see if you can cause to detect certain problems in code and fail to build if your static analysis detects them. All right, so that will be it.